All right, trainee, let's get you up to speed on reading these motion diagnostics. See all these squiggly lines? We're going to turn them into hard data, so pay close attention, all right?
Okay, so this is the question that really matters. I mean, it's one thing to say a car traveled, 100 kilometers in an hour. Easy. But what was its speed the exact moment it zipped past that signpost? See the difference? That's the gap between a blurry average and a crystal clear, instantaneous reading. And today, you're going to learn how to nail that reading every single time.
So here's the game plan. We'll start with the basics of velocity. Then we'll look at the easy stuff, straight line graphs. After that, things get interesting with accelerating motion and those curved lines. I'll show you how to pinpoint the exact velocity at any moment, and we'll wrap up with a quick review to make sure it all sticks.
All right, first things first. We got to be real clear on what we're actually measuring here. It's not just about how fast, it's also about which way.
Okay, so what is velocity? Look, in simple terms, it's just speed, but with a direction. Think about your car's speedometer. It just tells you how fast you're going, right? But velocity would say 60 kilometers per hour north. That's the key difference. For what we're doing, we're just tracking movement on a line, so our main focus is always going to be how much did the position change and how long did it take?
And this formula right here, this is our bread and butter. The big takeaway is that you always need 2 points, a starting point and a finishing point. You got to have a before and an after, both in space and in time to measure the change. This is the tool we'll be using again and again.
All right, let's start with the easy stuff, the warm-up lap, you could say. This is what the data looks like when something's moving at a perfectly steady pace. No fuss, no surprises, just clean, constant motion. Now look at that straight line. That's not just a pretty pattern, it's the graph talking to you. It's saying, hey, for every single second that ticks by on the bottom, I'm moving the exact same distance up. It's totally predictable, totally constant, super simple. So, how do we get the actual number out of this graph? Simple, we find the slope. Just pick any 2 points on that line, doesn't matter which ones. The vertical distance between them, that's your rise, or the change in position. The horizontal distance, that's the run, or the change in time. You just divide the rise by the run, and bam, that's your velocity. And for this particular graph, when you run the numbers, you get 15 meters per second. And here's the beautiful part. Because it's a perfectly straight line, the slope is the same everywhere. You could pick points at the beginning, the middle, the end, you'll always get 15 meters per second, constant velocity.
और अब आता है सबसे मजेदार हिस्सा। इस ग्राफ का जो स्लोप है ना, उसका एक सीधा फिजिकल मीनिंग है, और वो है वेलोसिटी। सोचिए कैसे, ग्राफ में जो वर्टिकल चेंज है, यानी ऊंचाई, वो क्या है? वो है दूरी में बदलाव, यानी डेल्टा एक्स, और हॉरिजॉन्टल चेंज, यानी बेस, वो है समय में बदलाव, डेल्टा टी, और डेल्टा एक्स बटे डेल्टा टी, अरे ये तो वेलोसिटी का ही फॉर्मूला है। कमाल है ना? तो प्रैक्टिकली इसे ग्राफ पर कैसे करते हैं? बहुत आसान है। लाइन पर कोई भी 2 पॉइंट्स चुन लीजिए। उनसे एक राइट एंगल ट्रायंगल बना लीजिए। अब बस उस ट्रायंगल की हाइट जो कि डिस्टेंस में चेंज है, उसे उसके बेस जो कि टाइम में चेंज है से डिवाइड कर दीजिए। जो भी नंबर आएगा वही उस चीज की वेलोसिटी है। सिंपल। इसका मतलब क्या हुआ? सीधा सा मतलब है, लाइन जितनी ज्यादा खड़ी होगी, जितनी स्टीप होगी, उसका स्लोप उतना ज्यादा होगा और वेलोसिटी भी उतनी ही ज्यादा होगी। और हाँ, ज्योमेट्री की भाषा में इसी स्लोप को हम टैन थीटा भी कहते हैं, जहां थीटा वो एंगल है जो लाइन एक्स एक्सिस के साथ बनाती है।
The average velocity between A and H can be found out by dividing hm by an. Similarly, the average velocities between B and G and between C and F are respectively Gn divided by Bn and Fo divided by Co. hm upon am equals tan theta 1, which equals the slope of AH, which equals the average velocity between A and H. Gn upon Bn equals tan theta 2, which equals the slope of Bg, which equals the average velocity between B and G. Fo upon Co equals tan theta 3, which equals the slope of Cf, which equals the average velocity between C and F.
Trainee, warm-up's over. Now for the real world. Because out there, things rarely move at a nice, constant speed, right? They speed up, they slow down, and on our graphs, that shows up as a curve. Let's figure out what that glitch in the data is telling us.
See, when that line on the graph isn't straight anymore, When it starts to curve up like this, that's a huge clue. It's telling you the object is covering more ground with each passing second, or, in other words, it's speeding up. It's accelerating. The velocity isn't constant anymore. It's changing.
Just look at this readout here. See how the curve gets steeper and steeper? Down at the beginning, near point A, it's kind of flat. But by the time it gets up to H, whoa, it's much steeper. That changing steepness, that's the changing velocity right there in front of your eyes.
And this is where we have to be super careful. This curve forces us to use two different tools. We can talk about average velocity. That's like saying the average speed for an entire road trip. Or we can talk about instantaneous velocity. That's the speed on your speedometer at one specific second. One's the big picture, the other's a precision snapshot. Two totally different jobs.
So, how do we get that snapshot? How do we pull the speed for one single moment out of a curve? This is where the real skill comes in, so watch this next part closely.
Okay, before we get to the tricky part, let's do the easy one first. The average velocity between point A and point H. We'll use our old formula. So, at point A, the clock says 1 second, and we're at the 5-meter mark. At point H, it's 8 seconds, and we're way up at 45 meters. So, the total distance covered, 40 meters, and the time it took, 7 seconds. You do the simple division, 40 meters divided by 7 seconds, and you get about 5.7 meters per second. But, and this is a big but, that's just the average over the entire trip from A to H. We know for a fact it started way slower than that, and it ended way faster. So here's the million-dollar question. What if the chief comes over and says, I don't care about the average. What was the speed exactly at point P? Our average calculation is useless for that. We need a new tool.
And here it is, the tangent line. Kisses the curve at that one single point, point P. It touches it, but it doesn't cross it. And get this, the slope of that tangent line is the instantaneous velocity at that precise moment. It's our way of measuring the slope of a curve at one frozen-in-time instant.
Now, if you're into the heavy math, this is what's going on under the hood. It looks scary, but all this equation is really saying is, let's imagine our 2 points for calculating slope get closer and closer and closer until the time between them is practically zero. It's just the fancy calculus way of saying we're zooming in on that one single point to find its slope. Okay, let's wrap this up. We're going to put our two main techniques on the table, side by side. You got to know which tool to grab for which job.
So here it is, plain and simple. You want average velocity, you connect 2 points with a line and find that line's slope. That gives you the big picture story over a period of time. You want instantaneous velocity. You draw a tangent line at one single point and find its slope. That gives you the right now speed. See, two different questions, two different methods. Simple as that.
All right, trainee, you did good today. You now know how to pull velocity from a position versus time graph. So I'll leave you with a little homework for your brain. If the slope of this graph is velocity, what do you think you get if you graph velocity itself against time? What would the slope of that graph tell you? Chew on that one. That's the next lesson. Dismissed.